Hi guys, Chapter 6 will be our lesson today. Chapter 6 is all about momentum. Momentum is the property of moving things. Remember, if it's not moving, it doesn't have any. Momentum depends on mass and velocity. You change one or the other, your momentum's going to change. It's a direct relationship, so if you increase mass, you're going to increase momentum. You increase velocity, you're going to increase momentum as well. Okay? Now, if you have a change in velocity, what is that? Oh, that is an acceleration, and we know all about that from studying Newton's second law, right? If you have an acceleration, then you have a net force. So, momentum, change, acceleration, net force, all that's rolled together and related to each other. Let's see how that works. Well, if you apply a net force to an object, like this guy pushing the gal on the bicycle, you're going to get a greater acceleration, which is a greater change in velocity, which means a greater change in momentum, right? It's like dominoes. Well, why do we study momentum? Collisions. Boom! Big collisions. Alright? Well, when you have a collision, it only lasts for a tiny little amount of time, right? But it can create this huge force. Okay? Well, when you have a collision, you have a sudden change in momentum, right? You've got a certain mass going at a certain velocity, and then bam! Right? Everything comes to a stop. Big change in momentum. And depending on how much time that impact lasts will depend on how big of a force you get, right? Okay? Well, that interaction is called an impulse. Right? In physics speak, it's called an impulse. So we can calculate that impulse as force times time or as the change in momentum, as we will see right here. So here's our two ways for calculating impulse, right? So we can calculate a change in momentum, and then if we know the time, well then we can use that relationship to get the force. Alright? It's all in there. Automotive engineers use impulse and momentum changes all the time to test crashes, right? What do you see right here? Big airbag in there, right? Well, what's that airbag doing? It provides you a cushion of air to slow down your stop, right? Big time, little force, right? And you live through the crash. Alright. Well, there's different ways we can have a change in momentum. First scenario, increase in momentum. Alright. So if we have an increase in momentum, that means we're going to have an increase in velocity, which definitely means there's an acceleration. And what causes an acceleration? Well, force. Alright? So to achieve the greatest increase in momentum, you need that force to be applied for the longest time possible. Right? You remember when you were learning to play sports when you were a kid? What did the coach always say? Follow through on your swing, right? Whether it's golf, hockey, baseball, right? Just like our little golf player right here. Following through on your swing gets you the most contact time so that you get the biggest change in momentum, right? Another scenario would be, well, decreasing momentum over a long period of time. Alright? This is kind of like the example with the airbag, right? You don't want a sudden stop, rib cage cracking on your steering wheel, head in the windshield, right? You want to slow down gradually. So that's what that big airbag, that big cushion of air does for you. Alright? It gives you maybe a second or two to stop instead of a fraction of a second to stop. Right? Bigger time, right? Bigger time reduces the force. Alright? Little time, big force. Alright? Because the change in momentum is the same. You're going some speed and then you stop. Change in momentum is the same. So this side of the equation stays the same. Alright? But depending on the cushion, which will provide the stopping time, will depend on how big of a force you get. Alright. Another scenario would be decreasing momentum over a short time. Alright, a perfect example of this is this Karate Kid girl right here trying to break the bricks, right? She has to have the bam, biggest force she can, right? So she's gonna be in contact for a little time, alright, to get the biggest force possible. Okay, well, momentum is special. It's conserved, which means the amount of momentum you have before an interaction has got to equal the amount of momentum you have after that interaction. You can't lose any, you can't gain any. Alright? Firing a cannon, which I've got in the picture here, is a perfect example. Right? So the interaction is going to be the explosion to actually fire the cannon. Right? So before the explosion, the cannonball and the cannon's sitting there, no momentum, right? Nothing's moving. Boom! You have the big explosion, cannonball goes flying out. Well, what does the cannon itself do? Well, it recoils a little bit, right? Jumps backwards for a little bit. Alright? And here's mathematically how that works out. Alright, and there's a little video there to help you with that too. Alright, but momentum is conserved because even though we had zero momentum before, the fact that there's different masses and different velocities of our two objects and they're going in opposite directions make those momentums cancel out. Okay? Now the way they can cancel out is momentum is a vector quantity. So remember that direction matters. Well, studying momentum is so we can understand collisions. Well, keeping in that vein, there's two types of collisions. Alright? Now, momentum is conserved no matter what. Alright? But knowing how the collisions work gives us a better idea of how to understand. Alright? So we have elastic collisions and inelastic. Alright? An elastic collision is when two objects will hit together but then rebound right off. Okay? No permanent deformation, no lasting heat due to friction of rubbing of the objects. It's just bam and then they bounce away. Alright? Perfect example. Right? Playing pool. Right? Pool balls. Just like in the picture here. Okay? Now momentum can transfer from one object to another. Right? But the total momentum in the system always is the same. Okay? So inelastic is the exact opposite of elastic. It's when you have two objects collide, bam, but now they stick together and move as one. Like my train cars here. Alright? Okay? They're the same mass. One's moving, one's still. Bam. Now they're hooked up. Now you've got double the mass. So look what happened to your speed. Mass doubled, so speed had to get reduced by half, right? In order to keep momentum the same. Alright? Here's how we can mathematically prove that. Alright? Now, momentum can be more complicated than that if we have objects going at angles to each other, right? That's where your Pythagorean theorem comes back into play, or using a parallelogram, because we're talking about vector addition again, right? But you can handle it. We know all about vectors. Okay? That is your introduction and your rundown of momentum. Alright, if you have any questions, as always, come see me.